Yeah. Hi.
Hey there.
What's up?
Hi. Well, this is Yochay. I know Yochay. We've met quite a few times through the years. He's with Lumus, and he's going to be speaking about their what they call geometric, or what I call reflective waveguides, and some new technology with it. So go ahead, Yochay,
Okay.
please.
I'll go ahead. I'm going to talk about geometric, which is also called reflective, but from the latest trend is to call it geometric waveguides. And specifically for micro LED, I'm going to compare that to other technologies and to other types of waveguides and do some very rough calculations. Um, uh, but it does not specific numbers. You can choose, your own numbers later on. Okay, so just as general, this is how a system looks like, which is a waveguide, has a projector that projects in some peripheral equipment, and and we actually produce evaluation kit that looks like this, but for the customer, we actually give the waveguide and the projector only. We call it optical engine. So, what is a waveguide? I'll review that a bit. And there are two main types of technologies being used. And one is the geometric, which I'll focus on in a minute. And that what characterizes is that all colors are projected and coupled into the waveguide. The beam propagate within the waveguide by total internal reflection, and then all the colors are reflected outwards. So since the all the colors red, green, and blue co-propagating the waveguide, it's the waveguide can support a large field of view. Just for comparison, diffractive works differently. You have a diffractive or a hologram or grating coupling in, create dispersion of the colors. Each one propagates a different angle, and then when they couple out, the grating creates a negative dispersion that actually causes the beam to co-propagate towards the observer, towards the eye. The issue is here that because the beams propagate at different angles, they consume much of the dynamic range of total internal reflection. Bottom line, you can inject a much smaller field of view, for example, in this single waveguide, and there's various ways to overcome that, but the simplicity of geometric waveguides enables very large field of view. I'll talk about that in a minute. So, how does a waveguide in generally looks like? It's you have a two-stage. One stage is in this example is example of Lumus waveguides, which is partial reflectors, as I showed before. But these ones reflect from the projector, total internal reflection in the waveguide, and then reflected while guided to the second section. And you can see it here in section 2, where the continuous reflection causes the aperture in the that projected the image into the waveguide to actually multiply. So if they like multiply apertures propagating in the waveguide, and then the second section, which is another set of partial reflectors, propagate it outwards. So you have actually multiplication of the aperture by 2 dimensions. Large aperture so you can see the image. Okay, how do we produce these waveguides? We talked previously about coating, so this is the know-how is how to design exactly the coating that enables, on the one hand, reflect the image towards the eye, but on the other hand, see the scenery, the see outwards. Then you stack these plates, slice them, polish them, cut the slice into shape. And the last thing actually not shown here is connect the projector into this waveguide. So that gives you just a general impression. Now let's dive into technology. So the main issue that's going to be interesting here is that the coupling in. The coupling in geometric waveguide is limited by the size of the waveguide. So if the width and the wider, the more you can project in. So it's relatively, let's call it wide. And for comparison, let's talk about the diffractive. We talked about the dispersion of the beams, and the main issue that limits the aperture of diffractive coupling into the waveguide is the fact that the reflected beam, let's see the blue here, must not hit the input coupler, because then it will couple back out and create scatter.